Hello friends. So we have been discussing parallel operation of transformers, right? And we have seen in the two videos necessary condition for parallel operation and desirable conditions of parallel operation. And these are very important topics associated with the parallel operation of transformers. Now that we have understood all these things, we have to now discuss how the equivalent circuit will look when the transformers are operating in parallel. So this is a basic diagram. And diagrams like these are not very useful as an engineer. You want an equivalent circuit of all these things so that all these things will go and you are having a proper equivalent circuit. Okay, so let me just draw a load here like this. So this load here is fed by these two transformers. So this is transformer A, primary, secondary, and this is transformer B, and this is the primary and secondary of that. Okay, so we'll be just taking the outputs of this because that is what is connected to the load. So we'll be only taking this end, the secondaries of the transformer A and B. Now you can clearly see the transformer dotted ends are connected together to this line here, and the undotted ends are connected to this line here. Okay, so these areas are common here. So what we can do is that we can replace this winding element by a voltage source. We can call it as E2A. Okay, so I'll just mark the polarities here. The plus is just indicating the dotted end and the minus the undotted end. Okay, so this is where this area is where the minus is connected. So now to the undotted end, the other voltage source is also connected. So this voltage source is E2B. Okay, and this also has a plus minus. Okay, and to the undotted end is connected to the dotted end together like this. Okay, now these transformers will have their own resistance and their own reactances, right? So we will just represent it by this resistance is Ra for the transformer A, and the reactance is Xa, and this is the equivalent reactance, okay, for the transformer. So this is the dotted end, right? So the transformer B also will have a similar thing, Rb, and this will be Xb. Okay, so the undotted ends are already connected together, just like in this diagram. See, the undotted ends are connected together, right? So the dotted ends also we can connect together like this. So these two are connected together. Okay, so both the dotted ends are undotted ends are connected together now. Okay, and these two together feed this load ZL. Okay, so these two together feed this load which is called ZL. Okay, and the total current to the load, let us call it as IL. Okay, the total current to the load, let us call it as IL. And each transformer will be giving its own share. Okay, so that we can call as IA from the transformer A and IB from the transformer B. So transformer A is supplying IA, transformer B is supplying IB. Now I have already told you, if transformer A is having higher rating as compared to transformer B, IA will be higher than IB. Okay, that is how the transformer you have to select. Okay, so this is the basic equivalent circuit of the transformer. Okay, now let us call this voltage across the load as V2. Now you can see that there are two loops here. One, you can start from here like this and you can end here. Okay, so the first loop will be E2A, RA, XA, the load, and back to E2A. Okay, so with that we can write a KVL here. So V2 will be equal to E2A minus IA into, so this together we can call it as ZA. Okay, IA into ZA. Okay, so RA plus JXA will be ZA. And the other loop we can see it is E2B, RB, XB and ZL and back to E2B. So that is the next equation. So again we can write V2 will be equal to E2A minus IB ZB. Okay, because IB is the current through the second transformer. Now clearly V2 is equal on both sides. So we can write E2A minus IAZA will be equal to this E2B. E2B minus IB ZB. Okay, so now we have seen in desirable conditions that this E2A should be equal to this E2B for proper parallel operation. So these two values, if they are equal, that is if E2A is equal to E2B, okay, we can just cancel these two terms here. So that means IAZA will be equal to IBZB. Okay, so that means this drop which you see here, that also is exactly the same. The drop across ZA and the drop across this ZB will be exactly the same. So we can just modify this circuit once again so that we can replace these two parallel elements by a single element and we can replace this by a parallel circuit. Okay, so what we can do is that we can make now it as a one circuit here. Okay, so this is a parallel connection, right? So that's not a problem. So E2A is equal to E2B Okay, and because the voltage drops across the both elements are same, I can keep it as a parallel circuit. ZA voltage drop is equal to ZB voltage drop. Right? So I can make it as a parallel circuit. So I can write it like this. So this is RA XA, and together they will be ZA, and this will be RB XB, okay, and together they will be ZB, and this will be to the load connection. Okay, basically we have just used some KVL and we have made a simple circuit out of it. So the current through the load is IL, that will not change. So the current here also will be IL. Now the current through this element will be IA, right? And IA ZA is equal to the current through this element is IB. So IA ZA is equal to IB ZB. Now see, these are parallel connections, right? So that is what we have fulfilled here. So IA ZA is equal to IB ZB. Okay, and IL vector will be equal to IA plus IB. Okay, IA plus IB. So these are the basic things that we have derived here. Now let us use the current division rule for this particular circuit here. So we can use the current division rule to find the value of IA. See, this is a simple parallel circuit, and if you remember your course on engineering circuit analysis, in this circuit we can easily find the IA and IB value using the IL value by using current division rule. So IA will be equal to how much? The total current IL multiplied by the impedance of the other branch, ZB divided by the total impedance, ZA plus ZB. This is the simple current division rule. So I'll write down that here. So this is the current division rule. Current division rule applied here. IB will be equal to the total current IL into the impedance of the other element ZA divided by ZA plus ZB. Okay, so this is also current division rule. Okay, now let us do some mathematics here again so that we can get an interesting conclusion. So let's use this particular equation first. So IA is equal to IL into ZB divided by ZA plus ZB, right? So what I will do is that I will multiply both sides by V2. Okay, so now I will get V2 into IA will be equal to V2 into IL multiplied by ZB divided by ZA plus ZB. Okay, so what is V2 into IA? We have already seen V2 into IA will be the apparent power rating of the first transformer, right? Apparent power of the transformer A, right? So V2 into the current through the transformer will be the apparent rating of the first transformer. Okay, so this I can replace this value by SA here. So SA. And what is V2 into IL? So this is V2, right? This is V2. So V2 into IL is the apparent power of the load. So I will just write it as S into L multiplied by SB divided ZB divided by ZA plus ZB. And this is one important equation here, especially for numericals. Now let us take this equation here. So IB is equal to IL into ZA divided by ZA plus ZB. Okay, so here also I will multiply it by V2 from both sides. So V2 into IB will be equal to V2 into IL multiplied by ZA divided by ZA plus ZB. Okay, so V2 into IB will be the apparent power rating of the second transformer. Okay, so this is SB. Okay, and V2 into IL is the apparent power of the load multiplied by ZA divided by ZA plus ZB. Okay, so this very similar to the current division rule. So this is used to find out the apparent power rating of the individual transformers. Okay, apparent power supplied by individual transformers. For example, if somebody gives you the apparent power of load is this, and they are given the impedance of the transformer, so you can easily find the load sharing done by both the transformers. Okay, so we'll just write down that here. So SA will be equal to SL into ZB divided by ZA plus ZB, just like the current division rule. And SB will be equal to, this is transformer B, SL into ZA divided by ZA plus ZB. Okay. Now the important thing here is that when deriving, this is based on the this ZA ZB are actual impedances of the transformer. They are the absolute impedance of the transformer. So ZA is the impedance of transformer A. Okay, and ZB is the impedance of transformer B. Actual values. These are not per unit values. Now in case in the question they ask per unit values. Okay, they give the information per unit values, and usually they give in per unit values. You have to be a little bit careful. Okay, so what happens is that, for example, a transformer has a impedance of 0.02 plus j 0.08. something like this. Okay, they give something value like this. Usually it is based on the transformer's own base kVA. Okay, in per unit value, you know that the base kVA is very important. So this is usually, for example, in transformer A it's given this value, and in transformer B it's given this value. So this value is usually, unless it is mentioned specifically, usually this value is calculated using the base values of transformer A, and this value is calculated using base values of transformer B. But to use this equation here, you have to bring everything in a common base here. Okay, so that is very important. So the existing per unit values, you have to convert it into another base. If you have not seen my video on per unit values, I strongly go and ask you to see those videos, because in those things I have videos I have explained this properly. Okay, so the usual formula that they use is that the Z new per unit value, okay, will be equal to the Z old per unit value multiplied by kVA base new kVA base divided by kVA base old, okay, multiplied by V base old divided by V base new, the whole square. Okay, so in this case, because the voltage ratings of the transformer in the parallel operations are exactly the same, the old value and the new value will be exactly the same, because you don't use transformers of different voltage ratings together. Okay, so these two values will be exactly the same. So this value can go. So this is the formula that we have to use. Okay, so this is the formula that we have to use. As an example, let us take a simple example here. For example, a 600 kVA transformer is there. Okay, and it has a Z APU of 0.06 plus J 0.08. Okay, so this is the per unit impedance. And another transformer is 300 kVA, and that per unit value of impedance is 0.08 plus J1. Okay, J1. So this is the per unit value. Now, if you want to use it in this particular formula, you have to convert it into a common base, because this ZPU is found using this value, and this value is found using this value. So here, let us take the common base as 600 kVA. So if you take the common base as 600 kVA, so this is the new base value here. Okay, so let's use the formula here. So for the first transformer, so ZAPU new will be equal to ZPU old, which is this value, 0.06 plus J 0.08 multiplied by new kVA base, which is 600 kVA, divided by old kVA base, which is also 600 kVA for this transformer. So that value will be exactly the same. So it is 0.06 plus J 0.08. Okay. Now, this is for the first transformer. And for the second transformer, ZBPU new, that has been found out using another base 300 kVA. Now you have to bring it to 600 kVA. So that will be also equal to the old per unit value, which is 0.08 plus J1, okay, multiplied by new kVA. What is new kVA? It is 600 kVA, right? I am taking new kVA as 600 kVA divided by old kVA, which is 300 kVA here. That is 300 value is equal to 0.16 plus J2. Okay, so while using in numericals, you have to use this value in this particular formula here, right? So if they have given the values in actual ZA, ZB, they have given actual value in ohms, you can directly use this. But if they have given in per unit values, and those values have been derived from their own base KVAs, that time you have to assign a common base KVA and recalculate this ZPU. Okay, so that is another important thing here. So now let us do a simple numerical to calculate the load sharing of transformers. In this, all these concepts will come. Now this is the numerical that we are going to do. So the load is given to be 400 kilowatt at 0.8 power factor lag. Two three-phase transformers rated at 200 kVA and 300 kVA are operated in parallel to supply this load. So the 200 kVA transformer has RA to be 0.02 and XA to be 0.04 PU. And 300 kVA transformer has RA to be 0.1 and XB to be 0.05 per unit. So you have to calculate the load sharing. So in the formula, you know that SA is equal to SL into ZB divided by ZA plus ZB. Okay, and SB is equal to SL into ZA divided by ZA plus ZB. Now if they have given the values in ohms, you can directly substitute everything and find the result, but they have given in per unit values. This RA and XA are calculated with 200 kVA as base, and RA and XB are calculated with 300 kVA as base. So to use it in this formula, you have to convert them into a common base. Before that, let us find the value of SL. So they are given that the power P is equal to 400 kilowatts, okay, and cos theta, which is the power factor of the load, is given to be 0.8. Okay, so now you know that from the power factor triangle, power will be equal to S into cos theta, right? P is equal to S into cos theta, simple result. So S will be equal to, in this case, SL is equal to PL divided by cos theta, and PL is equal to 400 kilowatts divided by 0.8, right? 0.8. So this is equal to 500 kVA. Okay, so SL value is equal to 500 kVA at what power factor? At 0.8 power factor. So that is the demand from the load. So we have to find out of this 500 how much will be given by 300 and how much will be given by 200. So naturally we know the higher kVA rating transformer will give higher contribution and the lower kVA transformer will give lower contribution. That we have already seen in the desirable conditions, right? So let us now do the calculation now to find the new per unit value of ZA and ZB. So what is that formula here? So ZPU new is equal to ZPU old multiplied by kVA base new divided by kVA base old, right? So this was the formula here. So now let us take a new kVA base. So we will take the kVA base as 300 kVA. So kVA base new, we are going to take it as 300 kVA. Okay, so for ZA and ZB we have to recalculate all the per unit values. So ZA per unit new will be equal to ZA per unit old multiplied by kVA base new, which is 300, divided by kVA base old, which is 200. So let's calculate this value now quickly. So we can substitute this value here. So ZA will be equal to 0.02 plus J 0.04 multiplied by 3 by 2, right? Multiplied by 3 by 2. So this value you will get it as 0.03 plus J 0.06 PU. Okay, so that is the value that you can use at ZA here. Now let us find the value of ZB. Okay, so we'll just write it here itself. So ZB PU new, that will be the same value only. So ZB PU old multiplied by kVA base new divided by kVA base old. Right, so that was the formula here. So old value is 0.01 plus J 0.05 for the B transformer, and the new kVA is 300 kVA. New kVA is 300 kVA, and the old kVA is also 300 kVA because it's a 300 kVA transformer. So that value will be exactly the same. Okay, 0.01 plus J 0.06. Okay, so we have all the values necessary to find the individual contributions of SA and SB. Okay, so what we can do is that we can write the formula here once again. SA is equal to SL into ZB divided by ZA plus ZB. Very simple formula to remember. SB is equal to SL into ZA divided by ZA plus ZB. Okay, and SL value was equal to 500 kVA at 0.8 power factor. At 0.8 power factor. So we can write it as 500 kVA angle. If you want, you can put the angle also. So you can put it as 36.86, right? kVA angle 36.86. And the ZA value was equal to how much? ZA value was equal to 0.03 plus J 0.06 PU. We found out it, right? We just recalculated it, and ZB value was 0.01 plus J 0.05 PU. Okay, so you can substitute these values here. So SA will be equal to 500 kVA. 500 kVA. You can put the angle also here. Okay, so because it's a vector problem, you can put the angles also here. So it will be 36.86 multiplied by 0.03 plus J 0.06 divided by this is ZB right here. On the top it will be ZB. For SA it will be ZB. So 0.01 plus J 0.05 divided by 0.03 plus J 0.06, which is the ZA value plus the ZB value. Okay, so if you calculate this value, you will get 217.9 kVA. Okay, at 0.881 lag. The angle will be 0.881. I am not doing this total calculation because it will be boring. You can do the calculation on your own because some work I think you also have to do. So this will be 500 angle 36.86 multiplied by SB is ZA, right? ZA will come. So it will be 0.03 plus J 0.06 PU divided by 0.03 plus J 0.06 pu plus total impedance, right? So this is 0.01 plus J 0.05 pu. So if you calculate this value, you will get as 286.3 kVA. Okay, if you add these two together, you will get how much? 500 kVA. Okay, you will get 500 kVA. You can clearly see SB was the 300 kVA transformer, right? It can go up to 300 kVA, and this was the 200 kVA transformer. Clearly you can see that 286 is greater than 217. That means the higher rated transformer is taking more load. Okay, that means the desirable conditions of the parallel operation of transformers has been fulfilled. Okay, so with this video we are concluding parallel operation of transformers. In fact, with this video we are concluding the total module of transformers. So in transformers, basically we have got an extensive course. I think there are around 80 or 85 lectures on transformers. I never thought that it will be such a comprehensive course, but once the course started rolling off, I understood that I had to cover a lot of things in depth. So basically you are having single phase transformers and three phase transformers, and everything has been dealt in depth. There are some topics which I have not done, okay, and some things I have done it wantedly also. Specifically in three phase transformer connections, I have not done Scott connection as well as open delta connection. Now these two connections I might do when I get time, but I have left it out because I want it to be done by you. Whatever knowledge we have acquired till now in understanding the transformers is more than sufficient to understand those two basic connections. Open delta connection is a very simple connection, and is so Scott connections. Other than that, so before doing all those connections, I strongly recommend you watch the three phase transformer connections videos properly, so that you know how to draw the vector diagrams of all these things. And once you draw the vector diagrams on your own, you will never forget the concepts in electrical engineering. Okay, so I would first of all like to thank all of you who have patiently gone through this entire course. A lot of effort has been put. Multiple books like Chapman, H. Cotton, and the book by Theodore Wilde, and as well as the Electrical Machinery Fundamental. There is another Vincent Del Toro. All these books have been referred in creating this particular course. And of course, in the WordPress page, you can find the short notes for all these things. The short notes are not as such very in-depth. Okay, these are just complementary to the video lectures. For example, you watch the video lectures and you forget some concept. If you have the short notes with you, you will remember them. That is why I prepare the short notes. But I strongly recommend that you prepare your own notes also, because that is the best notes that you can prepare. Rather than anybody supplying you notes, the notes which you prepare on your own is more important. So I again thank all of you who have patiently seen all these videos, who have provided a lot of encouragements by commenting in the videos, ask doubts, and also sometimes provide criticism of how I can improve the videos. Okay, so again I thank you all of you, and I request you all of you to please share these videos, because these courses are very extensive, and of course these are all freely available. If you have just an internet connection, you can watch these videos. There is nothing charged as such for you, not for the videos nor for the notes. This is just what I am doing to give back to the society which has brought me at this place where I am standing now. Okay, so that is the most important thing. Please share these videos to your friends and anybody who find these videos helpful. Okay, because there are other courses also in this channel, like engineering circuit analysis, DC machines, and synchronous machines, as well as transformers. So the transformer module is officially closed here. In case I find I have to discuss something, that I will do later point of time. So I am leaving you with three questions here. One is Scott connection, one is open delta connection. Another connection which I want you to do is not a connection. I want you to understand the difference between a power transformer and a distribution transformer. These differences can be easily understood if you have understood the course till this point of view. I always believe if you understand the parallel operation of alternators properly, you can understand most of the things in electrical engineering, because that is where a lot of concepts are involved. And once you understand all those things, anything understanding in electrical engineering is not very difficult. Okay, so again, I thank you all, and mostly we will be starting induction motors very soon. Please give me some time just to prepare a course structure of how to present the induction motors to you. And once the induction motors is over, the entire machines module will be over, and I will be giving it out. The videos will come online. Okay, so till I see you in the next video, it's me Varun signing off, and have a great day.